Great, we talked about an application of finding cool shoes or dresses just based on image features. The technique that we're going to use today is called deep learning. And in particular, it's based on something called neural networks. But before we get there, let's talk about data representation. We discussed things like TF-IDF and bag-of-word models, but how do you really represent data when it comes to images? These are called features, and this is a key part of machine learning. So typically, when we talk about machine learning, we're giving some input. Let's say we're doing classification. We talked about sentiment analysis. You're giving a sentence, it goes through a classifier model, and we decide if that sentence has positive or negative sentiment. In image classification, the goal is to go from an image, this is my input, the pixels of the images, to a classification. In this case, this was my dog, and I want to classify it as a Labrador Retriever as opposed to other kinds of dogs. So as we discussed, features are the representation of our data that's used to feed into the classifier. There are many representations. So for example, with text, we talked about bag of words and TF-IDF. With images, there's a lot of other representations, and we'll discuss a few more of those in this module. But today, we're really going to focus on neural networks, which provide a nonlinear representation for the data. Now, let's go back to classification and just do a little review. We discussed linear classifiers, which create this line or linear decision boundary between, say, the positive class and the negative class. And that boundary is stated by the score, W0 plus W1 times the first feature, X1, W2 times the second feature, X2, and so on. On one side, on the positive side, the score is greater than 0, and on the negative side, the score is less than 0. So if I have this nice score function, I can separate the positives from the negatives. In neural networks, we're going to represent such classifiers using graphs. And so here we have a node for each feature, X1, X2, all the way to the dth feature, XD, and a node for the output Y, which we're trying to predict. So the first feature, X1, is multiplied by the weight W1, so I'm putting that weight on the edge. X2 is multiplied by the second weight W2, I'm going to put it on that edge, all the way to XD, which is multiplied by the weight WD, which I put in the last edge. And the last weight W0 doesn't get multiplied by any feature, but it gets multiplied by the number 1, so we put it a little 1 at the top, multiplying W0. And so if you imagine multiplying the weights W0 through WD with the features X1 through XD and the coefficient 1, you get the score. And when the score is greater than 0, we declare the output to be 1, and when the score is less than 0, we declare the output to be 0. This is an example of a small one-layer neural network. So we describe the small linear classifiers as a neural network, as a one-layer neural network. What can this one-layer neural network represent? Let's take the function x1 or x2. Can we represent that using a small neural network like this? Well, let's define that function a little bit more formally. So what we have is variables x1, x2, and the output y. And there's some possibilities. X1 can be 0, X2 can be 0, and since it's X1 or X2, the output Y will be 0 in this case. When X1 is 1 and X2 is 0, the output is 1. When X1 is 0 and X2 is 1, the output is 1. And similarly, when they're both 1, the output is 1. So we want to define a score function such that the value is greater than 0 for the last 3 rows, but it is less than 0 for the first row. How do we do that? So for example, there are many ways to do it actually, but if I put a weight of 1 on each one of the edges, x1 and x2, and we think about the score of the first row is 0, and the score of the other rows are greater than 0. So we want to add a little bit of separation, so we might put a negative value on the first edge, let's say minus 0.5. And so let's see what happens to the score. When x1 is 0 and x2 is 0, then the score becomes minus 0.5, and yay, I have something less than 0, and my score is correct, my output is correct. When x1 is 1 and x2 is 0, I get a score of 0.5. Similarly, when x1 is 0 and x2 is 1. And finally, when they're both 1, I get a score of 1.5. So with the simple weights on the edges, I represent the function x1 or x2. Now, can we represent the function x1 and x2? Well, similarly, we can put weights 1 and 1 on the edges x1 and x2, but in this case, we only want to turn it on when both x1 and x2 have value 1. So instead of putting minus 0.5 on that top edge, we put minus 1.5. And if you fill out the table, just like we did with the first example, you notice that we now represented the function x1 and x2 using a simple neural network. So a one-layer neural network is basically the same as the standard linear classifiers we've been learning about in this course so far. So what can linear classifiers not represent? We said it can represent x1 or x2, and it can represent x1 and x2. But what's a function, a very simple function they cannot represent? Well, here's an example. There is no line that separates the pluses and minuses in this example. This function is called the XOR. I like to call it the counterexample to everything. So whenever you're trying to find a counterexample, first thing to try is XOR. Now, for this case, the linear features that we described are not enough, and we need some kind of nonlinear features. And this is when neural networks come to play for reals. And we'll see an example of that. So let's review what XOR is. So XOR has value 1 when either x1 is true and x2 is false, so not x2, or when not x1, so x1 is false or 0, and x2 has value 1. So how can we represent this with a neural network? Well, let's call this first term z1 and the second term z2. What we're going to do is build a neural network to represent not directly the inputs x1 and x2 to predict y, but they'll predict its intermediate values z1, z2, and then those are going to predict y. So let's take z1. How do we represent a neural network, one-layer neural network that can predict z1? We discussed that a little bit, but here goes. It's a little bit different than the case, the end case from before. Since we have to negate, we say not x2, we put a minus 1 on that edge, and we put a plus 1 on x1 and the minus 0.5, and there we now have a representation for z1. Similarly, for z2, we put a minus sign on the edge x1, this edge here, x1 to z2. We put a plus 1 on the edge x2 to z2, and a minus 0.5 on the constant edge. And now we represent z2. And the last step, if z1 and z2 exist, all we have to do is OR them. And we already know how to OR two Boolean variables. It's just 1, 1, minus 0.5. And this is an amazing time for us. We've now built our first deep neural network. Not super deep, has 2 layers, but it is a little exciting. We just built our first neural network. It was a 2-layer neural network, but in general, neural networks are about these layers and layers of transformations of your data. And we use these transformations to create these nonlinear features, and we'll see some examples of that in computer vision. Now, neural networks have been around for about 50 years, about as long as machine learning has been around. However, they fell in disfavor around the 90s because folks are having a hard time getting good accuracy in neural networks. But everything changed about 10 years ago because of 2 things that came about. First, there was a lot more data. And because neural networks have so many more layers, you need a lot of data to be able to train all those layers. They have a lot of parameters. We'll see a really exciting neural network of 60 million parameters. So we need a lot of data to train them. So we recently have come about lots and lots of data from a variety of sources, especially the web. Now, the second really great change that made deep neural networks possible is advances in computing resources. Because we have to deal with bigger neural networks and more data, we need fast computers. And GPUs, which were originally designed for accelerating graphics for computer games, turned out to be exactly the right tool to build and use neural networks with lots of data. So because of GPUs and because of these deep neural networks, everything has changed. And now they've had a lot of impact in the real world.